can use Zoom the 9th edition. They have good explanations from there. I think you can understand better.
We want his notes.
Want his notes, they are summarized.
At the first Zoom that we just want
Very
notes.
simple. It was just a suggestion.
Oh, ndiye imwe mwenua yalinga. Okay.
Zoom dash. No way.
Zoom.
Zoom da somebody no wino muntu wanga.
Okay, so we
It's up to you to
continue.
make the summary guide.
We continue.
Sir,
Yes, brother.
I'm asking for the notes.
No, I'll send the notes,
Yeah, disturbing you.
and the videos are recorded, so you still have access to the videos and the notes.
I'm asking for the notes. Everyone wants.
Okay.
Sir, how
So-
do you access the video?
Sorry, you access them on the
Okay.
channel. So there's a channel which you need to ask your admin for your group to share with you.
Oh, all right, sir.
All right.
We
so
can
we are saying-
continue, sir.
we are saying that the energy that electron has lost in moving from one energy level to the next energy level is a photon. Now that energy of that photon, we need to know what is the wavelength of that energy being emitted. So in order for us to know the energy of or the wavelength, sorry, of that energy coming from the photon, or of that photon which has been released, we go back to our first equation where we are talking of waves, where we said that the wavelength is equal to Planck's constant times the speed of light over the change in energy. Okay? Or change in energy is equal to Planck's constant times the speed of light over the wavelength. Then we make wavelength the subject of the formula, and we come up with this formula here. Okay? So we come up with this formula here. All right, now applying this formula with the change in energy.
I can't see.
Sorry,
I don't know if you can increase the font. I can't see
you can't see the font.
the font.
You're using your phone, madam.
Not.
Okay, so I'll still share, then you can zoom in. Is that okay?
Okay.
Okay.
Just
Let's
on
get
your
the
phone.
explanation. So the change in energy, we get the change in energy we did from this photon here, 2.117 times 10 to the power negative 18. Or if we're given a change in energy, or if we're given a change in energy at any point. Okay, so this calculation here is not using that example. Used another sorry, it's here 2.117 times 10 to the power negative 18. We're using the same example we calculated this side, and we just proceed. Okay, so the change in energy here was 2.117 times 10 to the power negative 18. We substitute it there, we factor it in, and we find that the wavelength would be 9.38 times 10 to the power negative 18 meters. Okay, so that is the wavelength.
The question, sir.
Yes, please.
Yeah, on the energy that we calculated in the previous clip. Yeah, there was a negative. Now here, why have you left out negative?
Okay, so if you read the first sentence there, sir, it says that the negative sign on the energy means the atom has lost energy. Okay, and is now more stable. Now that energy it has lost, the negative is just telling us whether it is a gain in energy or a loss in energy.
Okay.
Yes. So since it has lost energy, it's a negative sign. So we'll just get that negative sign and we'll ignore the negative sign because here we just want to see the energy that it had lost. Because we already know in our minds that it lost the energy in form of a photon. So immediately we say a photon, energy lost in form of a photon, we've already dealt with the negative sign. So we get the absolute value for the calculation. We ignore the negative sign.
All right, thank you.
Because you cannot have a negative wavelength.
All right, sir.
Okay, thank you. So there's a statement down here on the previous slide. It is saying, note for this calculation, which is the next calculation, the absolute value of change in energy is used. Okay, we will not use the negative one. Okay, we proceed. So another example where we are there's quantization in hydrogen, energy quantization. We want to know the energy from level 1 to level what and so on. So calculate the energy required to excite the hydrogen electron from level 1 to level 2. And also calculate the wavelength of light that must be absorbed. So the other side, it lost energy. So here it is absorbing energy. So calculate the energy at level 1. Okay. And also calculate the energy at level 2. And then using the same principle from the previous calculation, final minus initial. So the final is energy level 2. The initial will be energy level 1. Okay. So it is energy level 2 minus energy level 1 to calculate the change in energy. Okay. So you find that in this case, because it is gaining energy, it will be a plus sign, a positive sign here. 1.63 times 10 to the power negative 18. So here it has gained a photon. We want to know what is the wavelength of this photon which it has gained for it to move from energy level 1 to energy level 2. We'll make that calculation down here. Okay. Wavelength is equal to Planck's constant times the speed of light divided by the change in energy. Okay. All right. So as the electron becomes more energy bound, its energy becomes more negative. Okay. Relative to zero energy. Okay. So the further away it gets from the nucleus, the more energy it gains. Okay. So as the electron gets closer to the nucleus, it releases energy from the system. Okay. So a general equation for moving from one level to the final is what we've been dealing with. Energy level of final minus energy level of initial. Okay. So this is what we've been calculating so far. Okay, now we look at the Balmer series of hydrogen emission spectrum. It shows 4 different colored lines on the visible region. So the wavelengths are also different, and they can be predicted by Rydberg's equation. Okay, which is the one that we are doing. That was Rydberg's equation. So energy, where you relate the initial level of energy to the final level of energy in meters. The wavelength will be in meters. Okay. So this is how you predict the wavelength of the emissions by the hydrogen spectrum. So an example again, calculate the energy required to remove any an electron from a hydrogen atom in its ground state. So we're removing the atom from energy ground state. Ground state is energy level 1. Since we're removing it from the atom, it is going to energy level infinity. It is going further away from the atom, in short. So energy level for infinite, the infinite energy level is the final state. Okay. The initial state would be energy level 1, the ground level. All right, so performing that calculation, 1 over infinity, if you do 1 over infinity on your calculator, it should give you 1. Okay, minus 1. Sorry, it will give you 0. 1 over infinity will give you 0, minus 1 over 1 squared is short. 0 minus 1 is negative 1, isn't it? So since it's a loss in energy, we'll still have our negative sign because it is a change in energy. Okay. So when you multiply that negative times the negative 1 from 0 minus 1, we get a positive 2.178 times 10 to the power negative 18. So here we're still applying the same principles, only that for this a specific example, final energy is infinite. We are looking at infinity. Okay. Yes, madam, you raise your hand, you can ask.
Sir, kindly repeat, like just this same slide. I'm not understanding.
Okay, so on this slide, madam, we are saying that we are trying to remove an electron from a hydrogen atom in its ground state. Now, this hydrogen atom in its ground state simply means that the electrons are at energy level n is equal to 1. And since we are removing, we're not moving it, we're removing it from the atom. So it means that the final energy level will be infinity. That is why we have N1 is equal to 1. N final, N initial is equal to 1, N final is equal to infinity. Okay? So therefore, the change in energy will be equal to this here, this change. 1 over, remember 1 is standing for the atomic number, divided by the energy state, which is infinite, minus 1 over the initial energy state, which is 1. So 1 over infinity is 0. 1 over 1 squared is 1. That's what you have here. Okay. So Planck's this constant here, sorry, not Planck's constant. This constant multiplied by -1 gives you a positive. So it means that the electron needs to gain energy. Loss of energy will be negative. Gaining energy will be positive. Okay. So that electron needs to gain.
Why are you dividing n final by 1 and then n initial?
Okay. So if we go back to, I was trying to get back to this slide. Okay, so n squared. Are we together, madam?
Yes.
Z over n squared. That n squared is either the initial one or the final one.
Okay.
Yes, that is why we are dividing it by n final, n initial. It is z squared over n squared. So the n, instead of us going to calculate the energies separately, we can calculate it directly by saying n final, n initial. You could have used this method here of calculating the two energies and subtracting. If you're not comfortable with using integers, the negative signs and so on, it's better you use that way. Okay.
All right.
Okay, thank you. I saw others raising their hands. Okay.
No, it's okay, sir. You can continue.
Thank you. All right. So we've removed this electron. Infinity, remember, we are removing it from the atom. Okay. So quantum numbers, solving Schrodinger's equation for an atom results in many orbitals. Okay. Many, this sign is, I've forgotten the term. Okay. Yes, for that side, each orbital is characterized by a series of numbers called the quantum numbers. It describes the various properties of the orbital. So the principal quantum number are in integers, 1, 2, 3, and so on. So it tells us the size of the energy orbital as n increases. So those energy levels we are calculating for, so those are the integers we're talking about, the quantum numbers. Okay, the orbital becomes larger and the electron spends more time further from the nucleus and has higher energy. Okay, and less tightly bound to the nucleus. Angular momentum, which is L, the value L, it's also calculated in, it's also in integer form. So meaning we have negative values and positive values. It tells us the shape of the orbital. If L is equal to 0, then it's an S orbital. If L is equal to 1, it's a P orbital. If L is equal to 2, it is D. L is equal to 3, it is F. So this will relate when we come to the electron configuration, the periodic table, and so on. When we do that, you'll be able to understand these values. These will be given to you. You will not need to calculate them then. Then the magnetic quantum numbers are between values L and negative L. Okay. So this is an example here. N is equal to 1, L is 0, and so on. Number of orbitals. So this, for now, when you see it like this, you'd want to memorize, but eventually it will just become automatic. You will know this by heart. Okay. You know that if there's one energy level, there's only one orbital. If there are two energy levels, then the number of orbitals may be 4 because you have to add them. Okay. So when you sit down to read through this, you understand this better. Okay. So finally, let's get an example. For a principal quantum number n is equal to 5, determine the number of allowed subshells, okay, for different values and give the designation for each. So since we have a principal quantum number of 5, okay. Yes, madam, I've seen you raise your hand. And the sir.
Okay, sir. Yeah, a question before you proceed.
Yes, sir.
Yeah, like the principal quantum number and angular momentum number. So principal quantum number is just the same as energy levels, and angular quantum number the sub levels, or what?
Okay. So the principal quantum number, it tells us the size and energy of the orbital, which we said energy levels, isn't it? As n increases, the orbital becomes larger. Okay. Now the angular quantum number is the value for each n, for each energy level. Okay. What is the value? Okay. For each energy level, what is the value? What is the shape? So in short, the angular quantum number is telling us the shape in that energy level which you know of. So the principal quantum is the n, which is the energy level. But the shape of that energy level. Okay?
Yeah.
Okay. That is why you find that the values of L are telling us 0, 1. You've seen that the values of L, if L is 0, it is an S shape. It is an S shell. S shell and P shell, S shell, P shell, D, and F have different shapes. Okay. All right. So we have the S shell, we have the P shell, and so on. So this is an example telling us if the value of n is equal to 5, for example. So what are the values of L? Remember, the values of L start from n minus 1. Okay. From this slide here. Okay. Here, we are saying that the values of L angular starting from 0, n minus 1. Okay. From 0 up to n minus 1. So here, from 5 up to n minus 1, which is 4. So we have 0, 1, 2, 3, 4, up to 4. Okay. So meaning the shapes, 0, remember, is S, L is 1. When L is 1, that's P. When L is equal to 2, that's D. When L is 3, that's F, and so on. So when we come to electron configuration, we'll see how these electrons are sitting. But for the number of orbitals, remember we said n is equal to 5. So our table here only goes up to n is equal to 4. So if we had gone up to n is equal to 5, we would have shown this also. So as you revise, you should practice this, writing this kind of notation up to n is equal to 4. N is equal to 5, you do it later on when you do advanced chemistry. But for now, I think up to n is equal to 4, if you can do it, if you can even do n is equal to 5, it's okay. Unless maybe you are doing it now. Are we together? So this table is
Yes, sir.
for your revision. Okay, thank you. We've come to the end of our session. If there are no questions, any further questions, additions, okay, I don't know what other things you'd want to say, but if there is anything else to say that requires my attention, feel free to ask. If I cannot handle it, it means someone else will handle it in your group.
Before you go, sir, something else I want to ask. Sorry.
Yes, please.
Yeah, like infinite is like, is there any pattern on the calculator where
Okay,
it's saying infinite?
I don't have a
or-
scientific calculator now, but I'm sure there is somewhere I remember using my calculator where I pressed infinite. I've forgotten where it is. It's long since I saw a calculator. But try checking.
Okay,
Yes, try checking.
yeah, but it's
But it's
there.
there. Yes.
Yeah, okay. Okay, all right.
Okay. Any other question? Okay, thank you. Have a blessed evening.
All right, thank you, sir.
Excuse me, sir, before you
Yes.
go. Oh, sir, as I wanted to ask or to request from you, since okay, like most of us who have not been attending to the tutorials because of the platform, like it's much expensive, sir. I don't know. So we're asking if we can be using at least a cheaper one.
Okay, so when you mean by platform, you mean
yeah, as
you mean Zoom? Zoom or the
yes.
Okay, so which one is the cheaper one?
I think Google Meet is better than this one.
I think Google Meet is better for the receiver than for the sender, because Google Meet is like a phone call. So for you, it is better, but for me, it is difficult.
No.
Yes, but we'll try to see where we can meet so that we can, but that one can only be addressed by your admin for the group.
No, okay.
Yes.
Sir,
No, okay, sir.
I forgot to answer the question which was dealing with the mass. So the mass would be in kilograms. I think I've answered your question now. The mass would be.
Sir, I have a question.
Yes, please.
Sir, you talked of the channel where we were supposed to get the notes and the recorded videos from.
Yes.
Is it that who should we ask? Like, how are we supposed to the channel? The admin of the group.
Yes.
Okay. Thank you.
Sir, do you have a YouTube channel?
That's the same one I'm talking about. The admin will give you the link to that channel. That's where we are uploading all our. There are different tutors. I think that you've noticed. So for each tutor, they have their own videos. So you select from those videos, and whichever video tutor you're comfortable with, you go with that tutor. Okay, thank you. Have a blessed evening.